Hey everyone, welcome to the Chapter 17, Section 4 through 7 vodcast. So this section is going to be all about solubility, the solubility product constant, otherwise known as KSP, and the common ion effect. Please make sure you have your guided notes, and I hope you kind of skim through these chapters and these sections in your book first. Let's begin. So just a reminder of solubility. The thing you have to remember is that some ionic compounds are only partially soluble in solution, and that degree of solubility is determined numerically by something called the KSP, or the solubility product constant. And the KSP is just like your equilibrium constant. In fact, the larger the value, the more soluble it is, and the smaller the value, the less soluble it is. So if you have some random compound, kind of like X and A, and it's trying to dissolve and make ions in solution because it's ionic, think about that equilibrium. So think about your equilibrium constant. You always put the products on the top and the reactants on the bottom. So you're kind of already used to that. So if we have a lot of products, that means the numerator is going to be greater than the denominator. And if you have a lot of products, it means you have a lot of ions. So it's highly soluble. Now, if you have a small value, that means that the denominator is going to be large. That means that that reactant, the ionic compound, did not really fully dissolve or ionize. And so it's going to be poorly soluble. Now, if you think about taking a compound and throwing it into just a pure solution with nothing in that solution yet other than water, and you throw that ionic compound in there, it'll partially ionize. It'll be partially soluble. And then there's a maximum amount of ions that you can get inside the solution, and then it just won't ionize anymore, and so you'll be left with like a solid on the bottom. That is called a saturated solution. The solution is saturated with ions and it can't make any more ions. So at the atomic level, when you are at a saturated solution, the rate of the forward and backward, in other words, the rate of the ions going into and becoming a solid, is equal to the rate of ions popping off of the solid and entering into solution. So the forward and the backward rate is the same. In other words, you've got an equilibrium. All right, that's why we can determine that KSP value. But the purpose of this section is also to talk about something called the common ion effect. So what do you think would happen if you try to take this poorly soluble compound, like over here, right? It's not very, very soluble. What do you think would happen to that compound if we took that substance and we stuck it into a solution that already had, say, like one of the ions that this particular compound breaks into, already present in the solution? So if we take this unknown compound, we'll call it XA, and we talk about it dissociating into X ions and A minus ions, right? What if one of these ions that is in this solution, what if it's like the anion? Let's just pretend. And I want to stick some of this XA right here. I want to stick some more of that into solution, but it's already got like a bunch of A ions already in that solution. Do you think that'll have any effect in the ability for this unknown compound to dissolve? So in other words, do you think that this compound down in the bottom of the solution, do you think it's going to be able to ionize in the same way if one of the ions in the solution already is part of it? Well, think about Le Chatelier's principle. You have an equilibrium with this poorly soluble compound, right? So if I start off the solution with some excess of this anion already present in solution, if that ion is already there, think about the principle of Le Chatelier. If I add a product to an equilibrium, won't the equilibrium shift over to the reactant side? So the bottom line is that when you have a common ion in solution and you're trying to put an ionic compound that is only partially soluble, if you're trying to throw that into that solution, it's not going to be able to ionize nearly as well, because the equilibrium is going to want to shift to the reactant side. It's going to want to shift over to try to make some more of the unionized compound. All right? So, how does a common ion change the solubility of a substance? It's going to reduce the solubility of any substance. And how does that correlate to Le Chatelier's principle? Well, anytime you push and you add more product into a equilibrium situation, it's going to want to push towards the reactant side. And that's the basic idea of this entire section. Now, let's start taking a look at some of that math. This begins on page 739 of your textbook. All right, so let's jump right in, okay? It says solid silver chromate is added to pure water at 25 degrees Celsius. Some of the solid remains undissolved at the bottom of the flask. The mixture is stirred for several days to ensure that equilibrium is achieved between the undissolved silver chromate and the solution. Analysis of the equilibrated solution shows that its silver ion concentration is 1.3 times 10 to the negative 4 molar. Assuming that silver chromate dissociates completely in water and that there are no other important equilibria involving the silver ion or the chromate ions in the solution, they want you to calculate KSP for this compound. Alright, so we're starting off with Ag2CrO4. This is the substance that they put into the solution. And they are telling you that once the solution has reached equilibrium, that the concentration of this ion is 1.3 times 10 to the negative 4 molar of the, I'm sorry, not this concentration, my bad. This is what they put into solution. But this is equal to your silver ion concentration. Okay? Alright, so this is all the information that you get, and you are asked to calculate your KSP. Alright, so what you have, and you have to be careful because this compound, when it dissolves in water, you need to be very careful because you have 2 silver ions for every one of these compounds. So basically what you have is once this guy enters into water and it dissociates into 2 silver ions, right, because you see the 2 on the subscript right here, and 1 chromate, CrO4 negative 2, sorry. And these are dissolved, AQ, AQ. Alright, so your KSP is just like an equilibrium. You only are concerned about the products here because this guy is a solid, right? And solids really can't have a concentration because they're not dissolved, it's not part of the solution. So really, the only thing that you're worried about with your KSP are your products in this guy. So what you're going to do is you're going to take the concentration of your silver ion, and since you're making 2 of those, guess what you have to do? You have to square it. And then over here you're going to have your CrO4, negative 2 ion, and that's just to the first power. Okay? So in order to calculate KSP, we're going to need the equilibrium concentrations for your silver ion and your chromate ion. And luckily, you have the equilibrium concentration of your silver ion. What you need to realize is that whatever the concentration of this silver ion is, your chromate ion is going to be half of that. Right? It should be half of whatever that is. So, because for every 2 of these, you make 1 of those, right? So what you need to do is take this concentration and half it, divided by 2. So grab your calculators. I hope you have one with you. 1.3 e negative 4 divided by 2. And you should get 6.5 times 10 to the negative, let's see, 1, 2, 3, 4, 5. To the negative 5, this molarity would be the concentration of your CrO4 ion. Let me just triple check the book, make sure I'm doing okay. Yep, I'm perfect. Sometimes. Sorry, not all the time. Didn't mean to sound arrogant there. Okay, so for your silver ion, all you're going to do is plug in the 1.3 times 10 to the negative 4, but you've got to make sure that you square this. And then for your chromate, we're going to stick in the 6.5 times 10 to the negative 5. Okay? And be careful with your math here, and let's just make sure that we get the same answer as the book. E to the negative 4, we got to square that, and then multiply that by 6.5 e negative 5. Okay, I get 1 point, how do I want to round that? I'm going to say 10 times 10 to the negative 12th. And let me just triple check. Yeah, I'm good. There is your KSP value, and there's no unit on KSP, it's just a number. And there is the solution for sample exercise number 10. Okay, obviously we're going to keep going. I want to look at sample exercise 11. So let me flip back over here. Okay, this is sample exercise. Oop. Keep going. Here we go. Whoa. Go back one. There we go. This is sample exercise 11. This begins on page 740. So the question says the KSP for calcium fluoride is 3.9 times 10 to the negative 11th at 25 degrees Celsius. Assuming that KaF2, so calcium fluoride, dissociates completely upon dissolving at that, and that there are no other important equilibria affecting its solubility, calculate the solubility of KaF2 in grams per liter. So basically you're going from KSP to the molarity. Okay, or not molarity, but grams per liter. So that's actually the unit for solubility. So what they gave you is KSP, and they're asking for the solubility. So KSP is equal to 3.9 times 10 to the negative 11, or yeah, 11th, but they want to know what the solubility is. And the solubility of this guy is in grams per liter. That's what they're asking for. Okay. So for this problem, we're going to need to set up, because we don't know exactly how much technically would dissolve in a liter, we're going to need to set up an ice table. So for us, we usually like to write out the chemical equation for the ion dissociation. So we're going to start with calcium fluoride, F2, and since it's not fully soluble, we need to make sure that we indicate that. We got 2 fluoride ions, so make sure you do this. Okay. And here we go. Okay, initial really doesn't matter because the solid is not really included into the KSP anyway, right? But we can assume that the initials are 0 over here, and we are obviously going to gain a certain amount of x, but because of this guy's coefficient, we are going to increase by 2x on this side, okay? So this is just x and that's just 2x. Alrighty. Now your KSP value is basically multiplying the products, but remember to do the coefficients. So this would be Ca, and you have a coefficient of 2 on your fluoride, so you better make sure you square that. So this is what your KSP, what do we call this expression? This is what your KSP expression would look like. So all we have to do is plug in the appropriate numbers where it's indicated, okay? So basically what you have is 3.9 times 10 to the negative 11th is equal to x times 2x, be careful, squared. Okay? Alright, now if you do your math carefully, just stick that in there and that becomes a 4, stick that in there, that becomes a squared, but then you have an x on the outside. This is basically equal to, what is this, 4x to the 3rd power? 3.9 times 10 to the negative 11th. Alright, so the first thing you do is just divide by 4. 3.9 e negative 11th, divide that by 4. You should get 9.75 times 10 to the negative 12th is equal to x to the 3rd. Alright, and I'm pretty sure you can guess what you're going to have to do. You're going to have to do a cubed root. To the 3rd. To the 3rd. This just becomes x over here. Alright, so on your calculator you're going to have to be able to do a cubed root. And I think for you, let's see, my calculator is different from everybody, so you guys all have those TI fancy smancy ones. So you're just going to have to figure out how to do a cubed root on your calculator. Alright, so do the cubed root and you should get, let me check, I get about 2.1 times 10 to the negative 4th. Alright, so that's your value for your K. Go back to the original question. They want to know the solubility. What you just basically did was you figured out the molarity. Okay, that's what that's all about, is molarity. So for us, we need to realize that this is moles per liter, not grams per liter. So you need to go back and figure out the mass of this particular solution, what that would be. Okay? So you've got 2.1 times 10 to the negative 4 mole per liter. And we need to know in 1 mole how many grams are there. And this is the ion right here, or this is the compound, sorry, calcium fluoride. So all you need to do is just go back and figure out the grams for this one. This is, let's see if you do your math right, it should be 78.1 grams. Okay, do your math, and you will get 1.6 times 10 to the negative 7, or second, sorry, grams per liter. There's your final answer. Alright, so just solving for x is not enough for you. You need to make sure that you know what the question asked you for. There was one more step that I had to do to complete this problem. Alright, so that was sample exercise 11. Now we're going to be skipping over to page 742 to look at sample exercise 12. Keep going here, there we go. Alright, so this is sample exercise 12. This begins again on page 742. It says, calculate the molar solubility of calcium fluoride at 25 degrees Celsius in a solution that is 0.010 molar calcium nitrate. So guys, what this is doing is the common ion effect. Alright, this is like Le Chatelier's principle. So if you remember, with buffers, you can have like the common ion effect in buffers. Well, turns out you can have the same effect with ionic compounds trying to dissolve in water. Alright? So we are going to approach this in the same way that we would normally, okay? So we have a slightly soluble compound. We got calcium fluoride, and we're going to need the KSP value for that. So you're going to have to look that up, and when you do, your KSP for CaF2 is equal to, let's triple check, 3.9 times 10 to the negative 11th. Okay, now what is this equal? You got to remember what this is equal to. This is equal to the products, which for you is the calcium ion, just to the first power. But look at your fluoride. Remember, your fluoride ion has to be squared, okay? So if we set up an ice table for this particular dude, 2 and then 2F negative, you're going to have the common ion calcium. Because look what they added. They added some calcium nitrate. Nitrate we don't care about, but the calcium we certainly do. Okay? So for us, in our ice table, this doesn't matter because this is your solid. But you will have an initial concentration for your calcium ion. This is whatever they threw in. This will be 0.010 molar, right? Fluoride was 0 because we didn't have any of that. Okay? Now, some of this is going to dissolve and add to the calcium ion in this particular salt that's, you know, this guy's totally soluble. Don't have to worry about that. So you're going to be adding, who knows how much, but you're going to be adding a certain amount of calcium here. Now your fluoride ion, be careful because of the coefficient, you're going to be adding 2x to this. So now you've got 0.010 plus x for your calcium, and this will just be 2x down there. Okay, now remember what your KSP expression was? It's up here. It's right here. Here's your KSP expression. And so we're going to be filling this in carefully. What this will give you for your calcium ion, 0.010 plus x times 2x squared. Okay, does that make sense so far? Alright, here is the best part about this guy. Because his KSP value is so low, look at the KSP value, really small, right? Would you expect this x to be a considerable addition compared to 0.01? Do you guys remember the 5% rule? You remember that? It's the same deal here. So what you would do is you take the 3.9 times 10 to the negative 11th, divide it by 0.01, times it by 100. Oh guys, I hope you understand that that is so minuscule, tiny, 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 that we really don't have to worry about the addition of this x. So you get to simplify this by throwing this x right here out. So technically what you're left with is 3.9 times 10 to the negative 11th equal to 0.10 times 2x, and that would be squared, like that. That makes your job a lot easier, okay? So let's be careful here. Remember that this will give you 4x squared. This is 0.10. 3.9 times 10 to the negative 11th. Okay, so now hopefully you'll be able to solve a little bit better. Pretty easy stuff here, okay? The 4 and the 0.1 goes on the denominator of the other side, so let's see what that is. That's 3.9 e negative 11th divided by 0.1, and this is a quantity, 0.1 times 4. Close it. Alright, so you should get 9.75 times 10 to the negative 11th is equal to x squared. And now to solve, you just do the square root. Okay, so square root answer should give you, I get about 9 point, how do I run around that? Let's go 9.9-ish times 10 to the negative, count carefully, 1, 2, 3, 4, 5, 6, to the negative 6 is equal to x. Now what was x? What was the whole point here? They want you to calculate the molar solubility, that would be moles per liter, of the calcium fluoride. So is that what you just solved for? That's what you have to check. Okay, what was x? Basically is what you need to triple check on, okay? X is coming from the calcium ion. If you compare the calcium ion to the calcium fluoride, do we have to multiply anything? Do we have to divide anything? Because these x's are in the form of molarity. In the previous problem, we had to switch it to solubility, which is grams per liter. But luckily, since we're dealing with moles and molarity, you found the molar solubility. You're done. Alright, so 3.9 times 10. Oh, I'm looking at the answer in the book. Oops. Looks like I made a mistake somewhere. Oh, sorry. Okay, I see what I did wrong. Sorry, guys. This should be... Sorry, I messed up on my math. See how easy it is to mess up on your math? I mean, even I do it, okay? So don't feel too bad. This is why we always check our work. Alright, should be, 9.8 times 10 to the negative 10th. There you go, that should work now. Alright, so take the square root of that. 9.8 e negative 10. Close those parentheses up. Ah, there we go. Sorry about that. So this should be 3.1 times 10 to the negative 1, 2, 3, 4, 5 is equal to x. Now, are we good? Woohoo! Alright. Alright, so 3.1 times 10 to the negative 5, that is your molar solubility for this answer. Now, of course, you know I'm going to do part B, so let's clear this board. So now we're doing part B, where you're adding, let's see, this is the solution. So now your common ion has switched into the fluorine. Now this gets a little bit more complicated because if you remember in your ice table, it looks totally different, right? Alright, so just in case you forgot, Ca and then 2F, boop, boop, and ice table, doot, 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 doot. This guy doesn't matter. Alright, so calcium initial this time for calcium is 0, but fluorine, now you're going to have the 0.010 molar on this guy. Okay. The addition here is just plus x, but this guy is plus 2x. And so you're going to have x down here, and this will be 0.010 plus 2x. Alright, hopefully that makes sense to everybody. You doing okay there? Alright, so now the question becomes, dun dun dun, are you allowed to ignore the addition of 2x? Okay, that's the question you need to ask yourself. Are you allowed to ignore the addition of 2x? That's a tough one. But guys, if you remember your KSP is really, really, really tiny. It is 3.9 times 10 to the negative 11th. So even if it were 2x, the addition of 2x, I still think that that would be an incredibly insignificant addition to this particular molarity. So you are absolutely allowed to ignore this addition because of this initial concentration, okay? So really, we're throwing this part out. Okay? So, KSP, please be careful. Remember that it is, what is it, sorry, I throw this out, sorry. For your calcium expression, it's just X. But for the fluoride, don't forget, you're going to have to do what? Square it. It's so easy to forget to do that. Alright, so now we're going to plug in all of our numbers. KSP again is 3.9 times 10 to the negative 11th is equal to, let me go ahead and square that right now, 0.01 squared. So this is 0.0001x. Okay, let's go ahead and solve for that x. So 3.9 e negative 11 divided by 0.0001. Okay, hopefully I didn't screw it up this time. 3.9 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. Negative 7 is equal to x. Let me make sure. Woohoo! I didn't mess it up this time. Alright, guys. Now, remember, they were asking for the molar solubility. Molar solubility is linked to Ka. Ka has a 1-to-1 ratio with your Kf2, so you're perfect. No multiplication or anything required. Yay! Alright, that was sample exercise 17.12. Now, everybody, go to page 745. Let's do sample exercise 17.13. Okay, 17.13. Okay, predicting the effect of an acid on your solubility. Alright. So we talked about how the common ion works. We talked about how it kind of is like a Le Chatelier principle thing that you got to work out. Alright, so now acids can increase solubility for different salts. Alright, and it depends on the salt, it depends on the acid, and all of that stuff. So we need to very carefully analyze this question. It says, which of the following substances will be more soluble in acidic solution than in a basic solution? Okay? So we're going to analyze all of these separately. Well, let's go ahead and analyze your first one. Oop, sorry. Hold on. I didn't mean to do that. Okay. Okay, so let's analyze your first one. NiOH2. Okay. When this guy ionizes, let's take a look at what you get. You're going to get a nickel ion, but check it, you're going to get 2 hydroxide ions. Okay? So the question is, which of the following substances will be more soluble in acidic solution than in a basic solution? Okay? Well, for us, we can pretty much predict that it's going to be more soluble in an acidic solution Because, guys, if you increase the OH concentration, if you add more here, what is it going to do? If you add more here, think of Le Chatelier's principle. If you add more here, it's going to shift back to your solid. Okay? But let's think about it in the reverse. If you were to increase your H ion concentration, okay, so if I increase some put some H ion in there, guess what's going to react with it? This guy is going to react. So if I decrease or pull down the concentration of your OH, how is this guy going to respond? It's going to come over to fill that empty spot. This is Le Chatelier's principle. And so I hope you understand that if you add an acid, it's going to react with this OH ion and push the solubility this way to fill in the empty void. Basically, that's what Le Chatelier does. If you make a void, it'll fill it. But think of the reverse. If you add something to one area, it'll move in the opposite direction to get rid of it. Alright, so the correct answer for A, we would be more soluble in an acidic solution. Okay, so A. Alright, let's look for B. You have CaCO3. Alright, let's think about the equilibrium here. You got some calcium ion and you've got some carbonate ion. Okay, so let's think about how this would be affected, okay? Alright, let's think about the carbonate ion. Okay, this guy. If we throw some additional acid in there, the question is, would that be a significant acid? In other words, would it be a strong acid or a weak acid? So if I throw in some H plus ions to react with this, you need to remember that H2CO3 is a really weak acid. And since it's a weak acid, it's not going to ionize very well. Okay? So, let's think about the, let's see. Let me go back to the book and just triple check to make sure. CaCO3 dissolves in acid solutions because carbonate is a basic anion. Okay. Oh, okay, I see what it's doing there. They're showing you, this is kind of like Hess's law, when you combine all of the equations to make one final one. So hold on, let me show you what they're showing you. Sorry, I get a little messy here. CO3, -2. Alright, so if you add acid, the acid will try to react with the carbonate ion. So let's see, 2 H plus ions are required to react with your carbonate. -2. Or actually, this will... Hold on, sorry. Yeah, this will be an equilibrium. Okay. H2CO3. Now this, you need to remember, will... you can't make carbonic acid. Carbonic acid is extremely weak, and what it'll really do is keep going and make a little bit of water and CO2. Okay, you got to remember that. That's a little AP trick that they love to push on you. So if you look at the overall reaction, these are what are placed in form of this carbonate ion. So the overall reaction would be CaCO3 with the addition of an acid. This is how it should respond. You'll make some calcium ions and CO2 and H2O. Okay. Now, let's listen up. It says the reaction between the carbonate ion and the H plus ion occurs in a stepwise fashion. First, it's going to form your HCO3 -1 ion, and then it'll form your H2CO3, right? And H2CO3 forms in an appreciable amount only when the concentration of H plus is significantly high enough. So for this guy, it looks like CaCO3 dissolves in an acid solution because your carbonate is a basic anion, okay? So this one will definitely increase the solubility with the presence of an acid, because what you're basically doing is you're not worried about this anion, because you know it's going to react with the acid to make, basically it's making like carbonated water with the presence of a calcium ion in there. The calcium ion will just chill. But anyway, it'll make a weak acid. The weak acid will naturally decompose into CO2 and H2O. So with the addition of an acid, if you're depleting step by step, that's basically what they're telling you, is as you step by step deplete your carbonate ion, then the solubility can increase. Alright, so let's go ahead and do the next one. C. Part C. You've got BaF2. Alright, let's think about this one. Got barium and 2 fluorides. Okay. So for this guy, do you see any ions that would make you hesitate with the addition of an H+? You called it. Okay. When you add the hydrogen ion to this, you are going to make hydrofluoric acid. Alright, so for this one it says the solubility of BaF2 is also enhanced when you lower the pH or when you add an acid, because this guy is going to react. So fluoride ion plus a little bit of acid will make hydrofluoric acid, right? And this is a weak acid, doesn't matter, it just makes an acid. And so you are slowly depleting this from the equilibrium. And how is this guy going to respond? It's going to push more over. So the solubility will definitely increase on C. Alright, let's do D. AgCl. Alright, let's talk about this guy. You're going to make some silver ions and some chloride ions. Any of those you worried about with the addition of a hydrogen? Okay, you're probably thinking that the chloride ion will react with a hydrogen ion, right? But isn't hydrochloric acid, HCl, isn't that a really strong acid? So as soon as you make the acid, it's going to turn back into ions. Well, that doesn't do any good, because this ion is the conjugate base of a strong acid, okay? So as soon as you make it, it's going to turn right back into the ions anyway. So we really cannot deplete the chlorine ion fast enough, okay? So yeah, we'll have some acid in there, and yes, as soon as the acid reacts with the chlorine, guess what the chlorine is going to do? The hydrochloric acid will re-dissolve into the ions. So this ion isn't going anywhere, unfortunately. Alright, so D, the addition of an acid, will have 0 effect on this guy. Okay, and that's bad. We don't want that. So D is the one that messes it up. Okay? Alright, so that was sample exercise 17.3. More of a qualitative question. Okay? And now I want you to go to sample exercise 15. So I'm skipping 14. You guys can look that over. So sample exercise 15. Predicting whether a precipitate will even form. Okay. Will a precipitate form when 0.1 liters of 8 times 10 to the negative 3 molar lead nitrate is added to 0.4 liters of 5.0 times 10 to the negative 3 molar sodium sulfate? Alright. The first thing that I like to do is I like to actually see what the reaction would look like. Some people don't do this, like it's not traditional to have to look at the equation, but I'm so visual that sometimes just seeing this makes a little bit more sense. Na2SO4. So it's a double replacement reaction. I don't know if it's a double arrow or not, because I'm not really sure about whether or not a precipitate will form. So PB is now going to be paired up with SO4. This guy is positive 2 because there's 2 nitrates. This guy is always negative 2, so this is nice. And then the other product that you're going to get is sodium nitrate Sodium nitrate, anything with a sodium ion is going to be soluble, so this is your AQ. These are your spectator ions, and to balance it, I'll put a 2 in the front. Right, I like to see the reaction. Alright, so the problem asks us to determine whether a precipitate will form when these two salt solutions are combined. So we should probably figure out the concentration of all the ions immediately upon mixing of the solutions, and then compare those to the reaction quotient Q, to the solubility, whatever the Q value is. So we're going to put all the products on the numerator, all the reactants on the denominator, solve, right, with all those concentrations plugged in. Solve for that, and then we're going to compare the Q at that instant with the KSP. Okay? And if Q is larger than KSP, what does that mean? And then if Q is less than KSP, what does that mean? We'll talk about that when we get there, okay? So that is the very first thing that I'm going to do, is I'm going to go ahead and solve for the concentration of the ions that are in the solution. So let's start here. And let's go ahead and solve for these guys. Okay, so we got 0.1 liters, so 8 times 10 to the negative 3 mole per liter. And then we're going to multiply that by 0.10 liters. Okay, so 8 E negative 3 times 0.1. So this should be 8 times 10 to the negative 4. Duh, I could have done it in my head. Duh. So this is moles. So I went from molarity to moles. Alright, and now that I have the moles, I need to look at the final volume of the solution. So go back to the problem. You got 0.1 liters here. You got 0.4 liters here. What's the total volume? Total volume will be 0.50 liters. I just added those, okay? So now, let's go ahead and then divide this by 0.50 liters, and this will be the new molarity. So take that answer, divide it by 0.5. You could probably, I don't know, some of you smarty pants could probably do that in your head. This is 1.6 times 10 to the negative 3 molar. Okay, so when you look at the precipitate, you know that this guy was your precipitate, right? The lead sulfate. Really, the only ion that I'm concerned about is that lead ion. And it turns out that for every one of these, you will make one lead. So this really is the concentration of your Pb, your lead ion. Okay? So now, let's go ahead and do the next part. So you've got 5.0 times 10 to the negative 3. And this time you've got 0.4 liters. So 5e negative 3 times, times 0.4. 0.002 moles. But remember, the new volume is now 0.50 liters. So then divide that by 0.5. You should get 0.004 molar. Alright, so which ion are we worried about for this guy? We're worried about the sulfate ion. Make sure you triple check that the salt only has one of those, and it does. So this would be equal to your sulfate ion concentration. Alright, I hope we're all okay. Now, since this is your precipitate that's being formed, your KSP expression, I'm going to erase, let's erase right here. Your KSP, which we're obviously going to have to look up, would be the products, lead and sulfate. Those ions are the only thing that matters. So for us, this will be Pb plus 2 times SO4 negative 2. There's your expression. So we got to look up your KSP, but for now, whatever concentration you have at this point is what we're going to plug in. Alright, Q can be done at any time. And the Q just comes from these with a specific concentration at a specific spot plugged into these. So this one will be 1.6 times 10 to the negative 3. And this guy will be 0.004. So your Q value is actually calculated in the problem. So 1.6 E negative 3, and then we multiply that by 0.004. Looks like your Q value is 6.4 times 10 to the negative 6. Now, what is the KSP value for lead nitrate? Lead sulfate. We would have to look that up. Okay, so it looks like our KSP is 6.3 times 10 to the negative 7th. Alright, so basically what we're going to do is compare these two values. So is your Q larger or smaller? Your Q is larger than K, and what that means is that it is too much than what we expected. So for us, that is too large of a value for this KSP. And since we have more ions than is possible to dissolve, basically that's what that means, we have too many ions than can dissolve, then we will have a precipitate forming. Okay? So yes, a precipitate will be forming for this particular sample problem. Alright, we've got one more to go. One more sample problem. I want to do sample exercise 16, and that's at the bottom of page 751. Oops. Previous. Okay, here we go. Sample exercise 16 says a solution contains 1.0 times 10 to the negative 2 molar silver ion, and 2 times 10 to the negative 2 molar of the lead ion. Then it says when chloride ion is added to the solution, both silver chloride with this KSP and lead chloride with that KSP precipitate form in the solution. So you got two precipitates forming at the same time. Hoo-hoo! It's like a battle. And it says, what concentration of chloride ion is necessary to begin the precipitate of each salt? And it says, which salt will precipitate first? Oh, tough little question here, okay? So, first let's analyze, and I'm going to use your sample exercise to kind of lead us through here. It says, we are asked to determine the concentration of chloride necessarily to begin the precipitation from a solution containing silver and lead, and to predict the metal chloride which will precipitate first. So here's the plan. We're given the KSP values for your two possible precipitates, and it says using these and the metal ion concentrations, we can calculate what concentration of chloride ion would be necessary to begin the precipitation for each. Alright? The salt requiring the lower chloride ion concentration will be the first one to precipitate. Alright, so let's take a look at this problem here. So you have a KSP for your silver chloride. Remember, this is the expression, this is the number. Alright? So for us, let's look back at the initial problem, and they gave you the concentration of your silver ion right here. So we're going to plug that into this expression, 1.0 times 10 to the negative 2. The chloride ion, that's what we're trying to solve for. We want to know what concentration of the chloride ion must be present in order for the precipitate to start forming. So once the concentration of your chloride ion, when you see this, once the concentration of your chloride ion reaches 1.8 times 10 to the negative 8, a precipitate will form. Okay? Now let's go to the next one. You've got lead chloride. Now the difference here is that in this expression, you're going to have to square the chloride because it's PbCl2. Alright? So let's see what kind of difference that makes. And notice that your lead concentration is 2 times 10 to the negative 2 molar. And so that was plugged in right here. And look at this. Now you've got an x squared, which is cool, alright? Let's see what happens there. When you solve for your chloride ion, we need a concentration of 2.9 times 10 to the negative 2 molar to start making this precipitate. Alright, remember what they said. They said that the salt requiring the lowest amount of chloride ion will precipitate first. So which one is smaller? Bingo. So what salt will precipitate first? AgCl. And what concentration of that salt must be present in order for it to start? 1.8 times 10 to the negative 8. Alright? So any chlorine in excess of this very small concentration will start to cause the sodium chloride to precipitate out, and then finally the lead chloride will start to precipitate when the concentration is much higher, 2.9 times 10 to the negative 2. Alright, so we figured out the concentration of the chloride ion to initiate a precipitate for each of these, and we discovered that silver chloride would definitely precipitate out first. Okay guys, these are the only sample problems that I want to do with you right now. There is one pretty good one here that just basically ties everything together nicely on page 755. Now I don't want to make your podcast too long, so I'm going to go ahead and stop right here. You guys, if you have any questions or anything on this podcast or ever, you know that you are more than welcome to email me anytime, or even go to our podcast and start posting something there. Alright guys, adios, ta-ta, see you later.